Okay, so we're going to take a look at some modeling today of real-world data. We're going to talk about two really kind of distinct things. So the first thing that we're going to look at is how we can determine things like doubling time or tripling time without having to go through and do an entire complete process each time. So there's kind of a shortcut way to deal with that. So for this first one, what I'd like you to do is pause the video after I kind of give an intro here and try this question and see if you can figure out if you would actually have the amount that you need. So go ahead and pause the video. I want you to try it first because it'll make our discussion afterwards a lot more meaningful. So pause the video, try it, and then come back in. All right, so hopefully you pause and you're not cheating. Okay, so hopefully you realize the formula you should use is PERT because it's compounding continuously. So PERT would give us a way to be able to compute this. So one way that you could solve this and figure it out is, all right, so we can calculate this by knowing, well, we want to have $8,000 at the end. We're starting with $4,000, and we know it's 9.5% interest. We could just solve for t to figure out how long that would take. So first thing, remember your base is e, so we always want to isolate the base, divide by that 4,000. So that would give you 2 to the 0.095 times t. And then hopefully you guys are remembering the work that you would do to solve that. We would take the natural log on both sides, and I'm hoping some of you recognize what you could just type into your calculator, that you don't have to show the work that goes with this. But I will show it for the video purpose here. Bring down the exponent. So again, the reason we take that natural log is because our variable is in the exponent. Ln of e is 1, so then we're just dividing by that rate. So actually, for those of you that understand sort of this change of base shortcut, what you're typing into your calculator is natural log of 2 divided by the rate. And what you've discover is that it's going to be like 7.3 years. So no, you're not going to happen in 4 years. So you're making that comparison to the 4-year mark. It's more than that. I would not have enough money. Now, some people though, and maybe you did this as well, looked at it as an inequality. So thinking about it like this, that it's not just 8,000, it could be more than that as well, right? So if I ended up having 10,000, cool, I would still have enough money. And they solved it as an inequality. The steps are identical, but it would be the t value would have to be greater than or equal to 7.3 years. So again, you would still come up with that same determination. But a third way, which I think is kind of interesting as well, is some people just solve for what would you have at the end. So they substituted in what they started with, the growth, and then they just put in 4 years. How much would I have saved after 4 years? And just do that calculation. It's 5,000 and something. I can't remember what the number was for that. Let me double check and we'll calculate that. So I think that's 5849.13, I believe. So again, how do I make that comparison then? Well, 5,800 whatever dollars is not the 8,000 I need to make that. So lots of different interesting ways to approach this question. Now, let's get back to the concept of doubling then. In order to calculate just straight how long does it take for something to double, I'm going to go back to the work that you did to actually solve if you solved it this way. Natural log of 2 divided by 0.095, which remember is the rate, that interest rate. So when I'm looking at that, if I change the interest rate, I can still calculate how long it would take to double, right? Just natural log of 2 divided by that new rate. So I'm always ending up doing that same thing. If it was time for my money to triple, I would just change that to ln of 3. Quadruple, ln of 4. So you can really save yourself a lot of time if you realize that it's always natural log of 2 for doubling, that is, divided by the constant. So let's take a look for a population to double if that's my rate. Well, would it be longer or shorter than the one we just did? Remember, the one we just did had a rate of 9.5%. Well, 9.5% is going to double faster than 6.15, right? It's a bigger interest rate. So this one should take longer. So natural log of 2 divided by 0.0615, and I was coming up with about 11.3 years. So definitely should take longer. But the time to double, this concept of doubling is always calculated the same way. Natural log of 2 divided by the constant. Okay, so now we're going to switch gears dramatically. So what we're going to take a look at today is we're going to look at modeling things that could be exponential using your graphing calculator. calculator. So taking real data and doing that. So this data is all about world population in billions since 1900. So the first year in this table is 1900 through the year 2000. So it's over a span of 100 years. Now, if I'm going to enter this in my calculator, I'm not sure I really want to type in 1900, 1910. It takes a really long time. So instead, I started at 0 for 1900. That was my year 0. So if I want to put in 1910, that's 10 years past. So then I would have just a 10. It's a lot faster to do that. Now the population itself, this is from the UN population, they're given in these decimal values, so 1.65. But you have to be careful because that doesn't mean in 1900 it was only 1.65. That was in billions. So again, why did they do 1.65? Well, a billion has how many zeros? 9. Do you really want to record that many values when you're entering information? So it just makes more sense to write it as a decimal and then just adjust it with your label. But be careful then when you talk about what those labels mean when you interpret your model. Okay, so let's go ahead and talk about how we would get this entered on our calculator then. You're going to go to your stat menu to edit, and we're going to get in there and clear out, out your list. So if you have any numbers in there, clear them. Don't delete them because then the list is gone. What I'm going to have you do is go ahead and enter your X's in list 1 and then your Y's in list 2. And so X's would be the time, the years since 1900, and then the Y's are going to be the actual population in each of those years. So I'm going to have you enter it in there. Go ahead and pause the video so you can get those numbers in there. All right, so now we have our X's in list 1 and our Y's in list 2. We need to tell the calculator that we want to do a graph like this. We want to do a scatter plot. So we're going to go to second Y equals to our stat plot menu, and we're going to go to plot 1 and we're going to turn it on. And then scatter plot is that very first icon, so the one that's being displayed. And then look below and just double check that, make sure your calculator is saying this as well. Make sure yours are saying X's in list 1 and Y's in list 2. You have lots of different lists in your calculator. You have a lot of capabilities, so it's just asking you where you put your data. And then the marking is what it shows up on the screen. And again, you have multiple markings because you could have multiple sets of data that you're all graphing at the same time. The other thing before you graph is you want it to display nicely on your screen. So I need to go to my window and make some adjustments. It may or may not be set up for the data that I have. So for me, it looks like X's go from 0 to 100. So I'm going to make some adjustments here in my window. You can also do a zoom stat. I like to have a little bit more control over what my window looks like though, so I'm kind of like to do my own. And then the Y's, it's going to go from 0. And then let's see, what does my Y value go up to? I'm just going to say 6 because it's right about at 6, going up by 1s. And then make sure your Y equals is cleared out. Before you hit graph, I want to make sure you don't have anything in your Y equals that's going to make this look kind of weird. All right, you don't want other rogue equations in there. So that's what my graph looks like. Okay, so let's have this discussion about the model part. When you are trying to pick a best fit equation, you're going to have to tell the calculator which one you think it is that it's going to model. And what do I mean by that? So when I'm talking about the model, I'm talking about what kind of equation would best fit this data. Maybe not a perfect fit, but best fit. So what are some of the options you have? Well, it could be linear. Okay, straight line. It could be quadratic, a parabola. It could be cubic. It could be sine or cosine. It could be absolute value. It could be square root. It could be exponential. It could be log. We have all these parent graphs. It could be tangent, secant. We have so many choices. So when you take a look at this graph, I want you to think about what options that are out there and which you think best fits this sort of a shape. Okay, well, I'm hoping that you're netting out at exponential like me, but let's talk about why that is. There's some very distinct properties that make something exponential as opposed to other types of models. So first thing, this graph is curving, right? As opposed to a straight line, which doesn't curve. In a straight line, it's a constant rate of change. You're going up by the same amount every time. This definitely does not have that. So it's not a constant rate of change. We don't have a constant slope. Lines can definitely increase or decrease, so it's not that it's not growing. It's because the rate that it's growing is not always going at the same amount. It's not a constant rate of change. This graph actually curves, right? There's a curve to it, so there's not a constant slope. Okay, so what causes it to curve? Well, the difference between the Y values isn't always the same. It's really tiny here, but then the distance here is a little bit bigger. The distance there is a little bit bigger. The amount of change continues to increase. It gets bigger. So the reason that is, think about exponential equations, these y equals ab to the x. You're multiplying by something, right? Your variable's in the exponent. This is a percent increase or decrease. It's a percent change. You are multiplying by something. So if you take a percent of a bigger number, your value is going to get bigger. So every time you do that, the amount that it's going to increase is also going to grow. So the amount that it's changing grows. So it's a percent change, not just a linear situation, which is a constant rate of change where you're always going up by the same amount or down by the same amount. So it's definitely a percent change. The other thing that makes this exponential, and we have this sort of parent graph idea of an exponential, is what's happening at this end of the graph at the left. Exponential equations approach asymptotes. And in this scenario, it is very easy to argue that this graph would be approaching an asymptote of 0, because for population, it can't go negative, right? I don't even know what that would mean. So it's going to be approaching 0 as we go back in time here. So, which is very different than a lot of the other parent graphs we have. Not very many other parent graphs have horizontal asymptotes. This graph would definitely have a horizontal asymptote as you go back in time. So it's a very reasonable expectation. Okay, so let's go ahead and calculate what we think that this equation is going to look like then. So we're going to go to our stat menu, over to calculate, and we have lots of choices here. The one that you want, we're just going to kind of talk through some different options. Number 4 would be if it's linear. If you think your model, your equation, should be linear, if when you look at your points, then you would select 4. If you think it's quadratic, a parabola, you'd select 5. Number 6 is cubic, so an x cubed equation. Quartic is the next one. That's like that W shape. Number 8, linear, just a different kind of linear regression. Number 9 is ln, natural log, so if you think it's a log regression. And finally, 0 is the one we want. So don't ever arrow down. Again, just press 0 or arrow up. It's a lot faster. Now, my calculator is going to look a little different. All right, so for me, I don't have as updated a calculator maybe as you do for my emulator here. I'm just going to press enter. But what you probably have on your screen is something that says the x's are in list 1, the y's are in list 2, and then it says regression equation store. You absolutely want to do that if you can. I'll kind of talk through the steps if you want to do that. Get your cursor down to the store line. It's the third one down. And when your cursor is there, you're going to go to the vars button, which is right here. So go to vars. And then once you're in vars, you're going to arrow 1 to the right, which is y variables. And then press number 1, enter on that function. We want a function. And then you should have a whole list of different y's you can store it in. Go ahead and select y1 and press enter. And then what it will do is once it calculates the equation, it stores the entire thing in your y1 so you don't have to type it. So you're welcome. It'll save you some time. And then go down to calculate and press enter. And for me and everybody has a calculator that's saying what mine does, we should all end up with the same equation then at the end. The only thing that does with the store is it stores your equation in your y equals for you. So that again, when you get to the store thing, it's vars over to y variables, function, and then number 1. Okay, so let's go ahead and round out to 4 places. I really want to have a good representation of what this model is. So when you jot down the A and B values, let's make sure we have enough digits here so we can be pretty accurate. So I'm going to write out to 4 places for each one of these. All right, now let's talk about what all this means. This is really important that we understand the meaning behind all of these. Let's start with this number. What does that represent in this situation? Well, it's the initial population. So it's the starting population. And for us, that means it would be in 1900. That was our initial year. And it would be 1.4457, and then remember what your units were, billion. Now, I want you to look back at your table. The actual population in 1900 was not 1.4457 billion. It was 6.5. Now, 6.5 is the actual data value. Ours is a best fit equation model. So it's not going to match up exactly. You can't expect that those numbers are going to be exactly the same, but hopefully they're in the same ballpark. Okay, what does this number tell us? Well, first of all, it's bigger than 1, so it's growth. Awesome. So this thing is growing. And what rate is it growing? Well, it's 1.37% growth in population per, now let's be careful, we entered 10, 20, 30, those were years since 1900. Now some people think it's per decade then, because we put in only every 10 years, but if my data was per decade, then 10 years I would have entered in as a 1, right? 1 decade. 20 years I would have entered in as 2, or 2 decades, then 3 decades, then 4. I didn't do that. I entered in 10 years, 20 years, 30 years. So this is per year. So just be cautious on how you think that through. All right, then the x value. Well, what does the x represent in this scenario? Well, x is our years. It's years since 1900. So years since 1900. Then the y, the all-important y, the value on the other side is usually the final amount in one of these equations. Well, the final amount of what? Well, that's our population then. So it's the population in a given year. So if you graph this equation now, so if you go to your y equals, those of you that have stored it already, you're good. I have to actually type it in, so I'm going to go ahead and put it in. But for the rest of you, if you were able to store it, which is really slick, then you already have your equation. If you haven't stored it, like me, you're going to have to go ahead and just type it in. It's not that big of a deal, but saved you a little time. Go ahead and go to your graph now and see how well you think our equation matched. It's pretty good. All right, so it fits pretty well. It's a pretty decent model. So now we could use this model to project for any time. So I can actually calculate or predict what the world population would be in any future year based on this equation that I have. All right, so let's talk about that equation then and do a little bit of that. So now that we've discussed kind of what all these mean, what is the initial population? Well, that would be the 1.4457, don't forget your units, billion. What year does that represent? 1900, that's when our data started. And what is the rate of growth? It's 1.37% per year. So important that we have that time frame in there. All right, so let's do some modeling, some projecting. So could we figure out what the world population would be in 2050? That seems like a ridiculous time away from now, but it's not really that far. Definitely your lifetime kind of span here. So what would the world population, if it continues to grow at this rate, so we're making that assumption, what would happen? And this is kind of data proved over time that it's been growing like this. Well, first thing we're going to have to decide is what does that mean for x? So if it's 2050, how many years since this data started is that? Well, if we started in 1900, how many years past is 1900? Well, that'd be 150. So one way that I could do this is I can just substitute in to my model. Remember, x is time, years since 1900. I can just put in that 150, do the calculation. And when you do that, we'll just type it in, you end up getting 11.13, and remember that's in billions. That's a lot of people. So if you think about that, is it reasonable for a population to continue to grow at a percent increase like this? Well, eventually something bad's going to happen, right? We're not going to have enough resources, space, food, whatever it might be. So it's really hard to imagine that it would continue to grow. But currently, if you Google the world population, you can check it. Pause the video and check it. Go ahead and Google, because I know you have your phone out and you're probably texting somebody right now. Just kidding. No, you're not, of course. You're totally focused. When you do this, though, it's about 2 or 3, something like that, billion right now today in 2016. All right, so let's take another approach from that. What we used for that one was the calculate, or just doing the calculation from the equation. You use the equation. But you have the equation in your graphing calculator, right? So couldn't you just go to your table and check and see what it was at 150? Now let me give you a hint on how to do that a little bit faster. If you go to your table set, go ahead and start at 150, because I'm guessing most people's table is probably around 0. You do not want to have to arrow up 150 times to get to the value we want. So just go to table set, start it at 150, and then you can get that value as well. So 11.13. So it matches up really well. So your other option is to go to your table, check your x value at 150, and what would the y value be. And those numbers that you got from your equation versus the graphing calculator table may not be perfect, right? Because if you've rounded a little bit, or what equation you put in was rounded, it may not match up as nicely as this one did, but it should be super close. Okay, so we got a couple different models. Now here's the last thing that we're going to talk about today, and this is so cool. Remember how we've talked about that you can model equations either with the 1 plus or minus r to the n or to the t, whatever variable you want to use, or you can use e. Here's where we finally show how we can go back and forth between one and the other. This is so cool. All right, so this is the original equation that we've been talking about. This is the y equals ab to the x. There's no e in there. The base is just a base 10 number. Okay, this is how you transform it, and this is really neat. So instead of writing our base, I am going to replace in my original equation this 1.0137 with a new statement. I'm going to replace it with e to the natural log of 1.0137 to the x power. Now that may seem completely crazy. You know, that's kind of me though, right? We're going to try though and see why that is. Can you go back to your graphing calculator, go to your home screen. I want you to type in, what is the value of e raised to the natural log of 1.0137? Type it in. Press enter, and you will be amazed. Look at it, it's 1.0137. It's back to what we started with. Those two red boxes on the screen, they're equal, they're equivalent, so it's totally legitimate for me to do that. Now, what does that allow me to do then? Well, I can just evaluate what just that exponent is. So I'm going to type in just that part of it, ln of 1.0137. And I can actually get what that k value, that constant, would have to be. So when I rewrite this equation, then in terms of e, it would be 1.4457 e to the 0.0136x in terms of e. Now, why on earth does that work? What's the relationship between e and natural log? Well, they're inverses of each other, right? So if you do a function and then it's inverse, don't you always get back to the number you started with? So pick a number in your head. Pick an easy number. Okay, got your easy number? Square it. Okay, have your answer? Now square root your answer. You just got back to what you started with. Why? Well, because squaring and square roots are inverses of one another. So are e and natural log. So that's why we get back to that value. Now, the cool thing is when it's written in terms of e, I can look at this exponent and say, oh, yeah, I know it's growth because it's greater than 0, and it would be 1.36% growth per year. Now, go back to your graphing calculator, go to your y equals. I want you to type in y2. So keep our original equation we had, but type in your new equation. So 1.4457 times e to the 0.0136x. And I want you to graph that one right with the other one. And if you take a look, it's graphing the other one. Can you tell a difference? They're exactly the same. They're going to graph almost identical. So if you go to your table then, it's kind of cool to do the kind of comparison here. You can see how close they actually are. So they're not perfect, but they're pretty darn close. So you can model with either one. So we can model in terms of E or in terms of just a base 10 number. So pretty cool. We can go back and forth. So couple things today. Doubling time, natural log of 2 divided by the rate, and then how can we use our graphing calculator to model anything, but specifically today, exponential growth and decay.